organizing all the seminar and everything, and for having me. Sorry also to all the other speakers that I haven't been coming to essentially any of the talks. Somehow the seminar clashes a little bit with teaching, and today just like had to have a colleague come and cover my class. So sorry about that for everybody, and thanks for coming. Okay, so cut and paste invariants and invertible TQFTs. So this topic of cut and paste invariants is connected to what Renee was talking about last time, and it's also the same cut and paste invariants that Julie will be talking in I think in 2 weeks' time, next week. Well, pretty soon, 2 weeks' time. Okay. So same cut and paste invariants. I'm going to talk about a different aspect of the project, which is how they relate to, as the title says, invertible TQFTs. And yeah, so this is joint work with Matthew Schembauer, which was a student of mine. And it's when the time comes, I name more important names in this whole story. Okay, so since you're not supposed to memorize one talk and like try to remember all the details in like 2 weeks afterwards, I'm going to recap a little bit of like things that Renee already said, which is the kind of the warm up or the setup of what cut and paste invariants are, why are they important, what is the context. So you might remember that the initial context, the prehistory of cut and paste invariants was the most classical notion of scissors congruence was the cutting and pasting of polygons. And how did that go? Well, you start with a polygon, you cut that polygon into different pieces, and now, well, you have those pieces, and you're going to like shuffle them around and paste them back together. So, you paste them back together to form a new polygon. The thing is that this has some rules. For example, you're not taking pieces and putting one on top of the other. What you're doing is you're using those pieces and you're pasting them along the boundaries of each of the polygons. Okay, a little bit more formally, we have this definition. So when are two polygons cut and paste equivalent? So you have your first polygon, which is subdivided here into a bunch of like sub-polygons, and it's a union of that. And you would have another polygon Q, which is also subdivided. So you say that they are scissors congruent if you have this isomorphism from all of the pieces. Each of the pieces correspond, and then the only thing you're doing is, well, the picture is already very explicit. The only thing you're doing is just like moving pieces around and pasting them back. So again, one of the interesting aspects of this question, of scissors congruences in general, is understanding what are the invariants. So we know that it's been known for a very long time, that the only invariant in the two-dimensional situation, in the situation for polygons, is the area. So if two polygons have the same area, I am going to be able to cut them out into little pieces and convert one into the other. So in two dimensions, it's well known. It's a good property. So the only invariant is the area. So no one could go one dimension up, and that's what Hilbert tried to do. And it was like Hilbert's third problem is, the question is now, I go one dimension up, now I'm talking about three-dimensional polyhedra. And the question is the volume the only cut and paste invariant in dimension 3? And when he posed this question, he gave the question to his student then. And then immediately, well, it didn't take very long for him to get an answer. The answer is no. And then actually came up with a new invariant, which is now called the Dane invariant. And the most explicit example here is that if you have a tetrahedron and you have a cube and they both have the same volume, they still have different Dane invariant. So the answer is no. There's an invariant that detects that those two things, you can't chop up the cube and try to convert it into the tetrahedron. It's not going to work. Going up in dimensions a little bit more. Again, Renee mentioned all of this, but it's good to have a recap. In dimension 4, well, there's generalized notion of volume, generalized notion of then invariants, and Jensen proved in the 70s that these are the only cut and paste invariants. And now if you go even higher, well, even higher you're in trouble, because even higher in dimension 5, it's an open problem. In fact, it's a very, very hard open problem. So yeah, so this is like the classical motivation of Caesar's congruence in like geometrical world. If we think about manifolds, we also can have an analogous operation. So here is again a recap of what's cut and pasting on manifolds. So here on the right, you have the whole process. So we start with our closed manifold M. And just as before, we're going to chop this up into little pieces. So we do our cut. And now what's the result? So we do our cut along, it's on the slide, but it's very, very faint. So there's an indication there of a k-dimension 1 submanifold. In order for it to be like a, let's say like a clean cut or a good cut, you need that k-dimension 1 manifold to be framed. You need it to be a neighborhood around all of that manifold. And then if you cut along a framed k-dimension 1 manifold, what you're going to get is these 2 pieces. And the 2 pieces, well, the boundaries of those pieces. So this boundary is going to be diffeomorphic to that boundary over there. So what's the next step? Well, just as with the picture of the polygon, now you're going to have your pieces, you're going to like move them around, and then you're going to do some clever gluing of the boundary. So the rule for manifolds in the classical case is that you're going to glue the whole boundary to the whole boundary. This is in the classical case. René talked about variations of this that have our other definitions, but for me in this talk, we're going to stick with the classical situation. So boundary is going to be pasted completely to the other boundary using, well, some diffeomorphism. Let's call that phi. So you do get a new manifold, and well, the result is you started with a manifold M, and you like now have achieved a different manifold by doing this cutting and then doing a gluing via a different diffeomorphism. And you could say that M and the original thing and the new result are cut and paste equivalent. So essentially, you could have chosen phi, you could have chosen any other diffeomorphism. That's all going to work. So essentially, what's happening here is that cut and paste manifolds, you do the cutting, you do the gluing. It doesn't matter how you glue. You are going to get something that's cut and paste equivalent. Okay. So now this formalizes nicely into a notion of cut and paste groups. So first of all, you have a monoid of diffeomorphism classes of smooth, closed, oriented, n-dimensional manifolds. That's a monoid under disjoint union. And then, well, then you can quotient by take the Grothendieck group and then quotient by this relation, which is the cut and paste relation. You're taking all your manifolds and quotienting by the relation that we just established in the previous slide, and which is what? Which is that, well, you have 2 pieces. You have one piece and you have another piece, and those 2 pieces are going to be identical on the other side. But then you can choose however you want to glue. You can glue via phi, or you could glue via something else. Those 2 things are going to be put in the same class in this group. And just to like make clear the notation, both my phi and my psi here are orientation preserving diffeomorphisms of the resulting boundaries when you've done the cut. Okay, so this is an important step along the way. The definition of these groups is well, one of the important ingredients of today's talk. So just to give a little bit of a flavor or like an extra example of something interesting that you can do with cut and paste invariants is, well, here we have on the whole slide, we have again the same game as we had at the beginning, we start with a manifold, closed manifold. Now I'm going to chop it up into different pieces, just as I did with the polygon. I'm going to rearrange those pieces. And finally, I'm going to do the pasting. Okay, and then what do we see from this whole process of cutting and pasting? So what we see is that the torus that I started with becomes with like a valid cut and paste operations. It's going to be in the same class. It becomes just 2 tori. So, you know, if the torus is going to be equal to 2 tori, that means that tori in the cut and paste group are going to be 0. So this example in particular is drawn and phrased here as a 2-dimensional example, as a 2 torus, but this generalizes to any mapping tori. So anything that fibers over S1 will be 0 in the cut and paste group. Just following this picture, you could think of it in like higher dimensions or with like different gluings. You do get that anything that fibers over everyone, any mapping torus, is 0 in the cut and paste group. Right, so again, like mimicking the situation for the polyhedra and the polygons and the polyhedra, now you can ask yourself, what are the cut and paste invariants? So, okay, so we know that cut and paste invariants are going to take manifolds that are cut and paste equivalent, and you're going to feed that into your invariant, and you're going to get the same result. So that's exactly what's happening in this little equation right here. So my lambda is a cut and paste invariant. These 2 manifolds, well, there's a cut and paste equivalent. The pieces are the same. The diffeomorphisms are different, but that's okay. The invariants do not notice how you've done the gluing. So now you feed that to your invariant, and it has to spit out the same number. So the difference is going to be 0. And as René already explained, the 2 essential cut and paste invariants are the Euler characteristic and the signature. And then essentially those are the only 2 essential ones. Everything else is linear combinations of the Euler characteristic and the signature. So so far it was a little bit of like a review of what René already explained. Like from now on, now I need to introduce a different group of invariants, which is a little bit more general in a sense. So the new group of invariants, sorry about that. Yeah, I call the SKK invariants. So all of these names, even SK comes from German, schneiden, it's cut, kleben is paste, so cut and paste. The extra K in the SKK is schneiden und kleben. The extra K is for kontrolliert or kontrollierbar, which is that you can control, you have some control of the invariants. How do they differ from the original SK invariants? So what are SKK invariants? So this line right here, I think that my pointer isn't quite working, but so that's why I keep drawing things on the slide. So so this slide right here, that row is supposed to be an SKK invariant. So what does it do? So it's actually taking again 2 cut and paste equivalent manifolds, and now you are evaluating this slightly more flexible notion of a cut and paste invariant, and what you're getting is not exactly 0, so you don't get exactly the same result, but you get a certain error term. And that error term, very importantly, is controlled. That's where the second K comes from, that kontrollierbar. It's controlled, or it only depends on the diffeomorphisms that you've used to glue your pieces. So this error term right here will be we can express it as some error term that only depends on my phi and on my psi in that case. And by allowing this flexibility, well, we get a lot more invariants. So obviously the error term could happen to be 0, and then you would be back to like the original cut and paste invariants. So essentially like the original cut and paste invariants are still going to be SKK invariants. That's when your error term happens to be 0. But you do get a lot more. You also get Bordism is a cut-and-paste invariant, and very interesting invariant as well. The Kerber semi-characteristic is also a cut-and-paste, an SKK invariant. The Kerber semi-characteristic is pretty much like a slight, well, it's a modification of the Euler characteristic. It is meaningful when your manifold is of dimension 4k plus 1. And what you're doing is you're taking your Betty numbers and adding them just up to the middle dimension, all the way up to 2k. If your manifold is dimension 4k plus 1, all the way up to 2k. And then whatever your result is, you're taking it modulo 2. So that is that's how you compute Kerber semi-characteristic. And that's one very interesting part of the story, as we will see in a second. So yeah, so lots more, a lot more invariants. In particular, all Bordism invariants are actually SKK invariants as well. So okay, so relation invariants. We also have a notion of a group, just as we had an SK group. We also have an SKK group. It's defined similarly. You also start with the same monoid, the monoid of diffeomorphism classes of oriented n-dimensional manifolds, closed manifolds. So you exactly the same thing. You also take the Grothendieck group, and you're also going to be quotienting out by a certain relation right there. And the relation is a little bit more complicated than the SK one. So let's say that you have more pieces to play with. So let's digest for a second what we are having on this line right here. So essentially what you can see here is this first M1, M2, and then there's like another M1, M2 right here. So you could say that those are SK equivalent, but then you also have this other component, which is M3, M4 with psi, and this is a SK equivalent with that. Not only that, so if I just say that, then we will be missing an important detail. An important detail is that all of these pieces, M1, M2, M3, M4, all 4 pieces have diffeomorphic boundary. So one important thing to notice is that over here, the phi is gluing M1 and M2, but on the other side, that same phi is being used to glue M3 and M4. So, and same thing with the psi. The psi here is being used to glue M3 and M4, and on the other side, it's been used to glue M1 and M2.
Excuse me, what does the bar on top of?
Sorry, yeah. So that is like I didn't say, but it's also important. We're in the world of oriented manifolds. The theory is also known for unoriented manifolds, and Renee and a collaborator, they're thinking about other tangential structures, which I think it will be a super interesting idea. But yeah, so that is just to indicate that like that keeping track of like your orientation so that you end up with some oriented manifold in the end. So that's the bar is the opposite orientation.
Okay, that's what I suspected.
Yeah, exactly. So the bar is the opposite orientation, and you need to keep track of these things. You're working with oriented, and you're having orientation preserving diffeomorphisms, and you have to keep track of which one is which. So the example is well, it's one of the many examples you could do with these pieces. I kind of tried to indicate the difference in the pieces by putting holes in them, and what it tries to highlight is this notion that you have the same pieces on one side, on the other side. So when you do your relation, you keep the same pieces. You're just kind of like swapping your diffeomorphisms, and you can do that because all the boundaries are diffeomorphic. And yeah, so now you have a slightly more difficult relation, but you can establish it, and then you are getting what's called the SKK group. Okay, so now how does the SKK group relate to cobordism? Okay, so it does relate via a short exact sequence, unlike SK, which does not relate at all to cobordism in a direct way. SKK does. In fact, it surjects onto cobordism. So you take any manifold in your SKK, and then well, that will go into its, it will map to its cobordism class. We do have a kernel. So the kernel is pretty interesting. The kernel is generated by spheres, not just spheres, but it's generated by spheres, meaning that any two cobordant manifolds will differ by a certain number of spheres when you look at it in the SKK group. And that's a longish argument, which I'm not going to reproduce right here. It's not terribly difficult. It's done in the original reference by Karras, Craig, Neumann, and Osa. It's done in there. And it essentially is just a little surgery argument. It's quite basic, but it's quite long to reproduce. So we're not going to go through that, but it is true. Any two cobordant manifolds will differ by some number of spheres when you look at it in the SKK group. The kernel, well, the kernel then has to be generated by spheres, which obviously go to zero when you do both when you do both morphisms. When you go to the cobordism, spheres are going to go to zero. One can interpret this kernel as the integers quotiented by this subgroup generated by all Euler numbers of n+1 dimensional manifolds. And then you can do your computation, and what you get is this nice computation of what the kernel is. So C when you are in dimension 4k, Z2 when you're in dimension 4k plus 1, and then 0 when you're in dimension 4k plus 3. So in those dimensions, SKK and cobordism will coincide.
Carmen, where is the case 4k plus 2?
Oh, I did forget that one. Yes,
the top one should be mod 2.
It's I think it's oh yes, I forgot that one. Sorry. I hope I'm not mistaken. It goes in there, right?
Yeah.
Yeah. Okay. Good. Thank you. Good. Well, one more thing I should say here before I move on to the next slide. There is the red arrow, which already appeared at the beginning. The red arrow. This sequence always splits. And that's one thing that I want to talk about in a second. So that one sequence splits. Obviously, when you are in the n equals n, like the 4k plus 3 situation, it's just trivial, the same group. If you're in the 0 and 2 mod 4, it splits via the Euler characteristic. And then this one is super interesting. That splits via the Kervea semi-characteristic that I mentioned before. And we're going to see an example right now of how that works. So let's look at the sequence in dimension 5. So this is one of the interesting ones, one of the 4k plus 1 situations. So we're going to look at it in dimension 5. Okay, so in dimension 5, we know that the cobordism groups are generated by the Wu manifold. So that is just Z2. We also know from the previous slide that my kernel over here, since I'm 5, I'm in this situation, like the 4k plus 1 situation, so I know that it's Z2. The sequence splits, the group in the middle is just Z2 plus Z2. So that's the plain computation of what these things are. So Wu manifold in the cobordism, spheres in the kernel, and then let's see how we can interpret the generators for the C2 and the other C2 in the SKK. So let me put this up. Okay, so lots of information in one go. So let's go step by step. So let's start with let me point. So let's start with this first one here. So with this mapping torus right here. So as I said, the generator in the usual generator that everybody names as the generator in the cobordism in dimension 5 is the Wu manifold. But the Wu manifold is also cobordant to this mapping torus, which is constructed by taking CP2 cross I, and then your identification, which is marked in red right here, the C bar, is supposed to be complex conjugation. So the result of that construction, that mapping torus of CP2 with the complex conjugation is actually cobordant to the Wu manifold. You could have chosen that as your generator of the cobordism in dimension 5. In fact, if you take that is in fact detected to be non-trivial by Stiefel-Whitney numbers. And you can do the computations of what the homology groups are. You can do computations of what the Stiefel-Whitney numbers are, and you do get this result. There is, by the way, a lovely, very, very nice math overflow post by Achim Krause. Julia, help me. Is that the right spelling? Achim Krause? Okay.
That's correct.
It's a really well done math overflow post on exactly like computation of the homology and cohomology of that mapping torus, and some computations on with the it is essentially it's an exercise, but it's such such a nice exposition that it's worth taking a look. Right. So okay, so that's one of my Z2s right here. That's the Z2 that gets sent over to the cobordism. What about the other C2? Well, the other C2 is just the trivial mapping torus. So it's going to be again CP2 cross I, but now the gluing is done via the identity. So that's just well, it's a trivial mapping torus. That is just S1 cross CP2. Okay, now a little less difficult than what Achim Krause did. Now you can just use the Keynote formula to compute the homology of this. And let me maybe scroll back a little so that we have the formula. Where was it? It was just here. Maybe I will just copy it. So we had our formula for the semi-characteristic. Okay, so we have a formula for the Kepler semi-characteristic here, so based. So essentially the homology of that is just Z all the way. So what you're going to have is C plus 1 plus 1 plus 1, you get 3. So you're getting that the Kepler semi-characteristic of this manifold, of that trivial mapping torus, is 1. So on the other side, like the splitting of the exact sequence via the Kepler semi-characteristic happens there, and the kernel is then detected by that, or it could be represented by that mapping torus right there. So this is one of the nicest situations, I guess, that when you go up in dimensions, it gets a little bit complicated. But here it's very visual, and it's super nice to understand these two, how this C2 plus C2, the generators, how they can match also nice geometric interpretations of the generators on both groups, on both sides. Okay, so that was my example. And then, okay, so as it turns out, this is a very interesting group. Of course, it's suggested onto cobordism. And there are other interpretations in the literature of SKK. So SKK, let's put it that way, is kind of like the most geometric one. But there are other interpretations. It's also it coincides, and this was proved very, very long ago by Janisch, that it coincides with Reinhardt's vector field bordism groups. So that kind of came from a different part of the story. Reinhardt was just trying to create some cobordism groups that had the Euler characteristic as an invariant, and it turns out that these things coincide. Fast forward quite a long time in history, the SKK groups also have a homotopy theoretic interpretation, as pi naught of the MTSO spectrum. Okay, that's we start moving. Okay, we're back. Okay, so we have this homotopy theoretic interpretation of something which we've interpreted like SKK is very geometric. Pi naught of MTSO is, you need homotopy theory to understand that. And this is already leading us a little bit towards the actual title of the talk. So we are going to relate the invertible TQFTs with these SKK invariants. And you could say, well, why not relating them to other interpretations of the group? Well, that is the right way to think of it. Like there is a lot of work done in the relation between the more homotopy theoretic interpretation and invertible TQFTs. There is quite a lot of work done. I'm pretty sure that's I'm going to be missing out like several authors, but one of the very important references understanding all of this, the MTSO spectrum and the invertible TQFTs, or one very good reference to look at that is a paper by Chris Schomer Breeze. And that's kind of like one side of the story.
Excuse me, did you say what you mean by MT?
Oh, that's, I'm not really going to go into that. I'm just kind of pointing out that there are different interpretations. This is the Madsen-Tillman spectrum, and it is related to the MSO spectrum in some senses. So yeah, it is a cobordism spectrum. You could interpret it like that. Maybe Renee, you're the expert on this. Do you want to add any comment? I'm going to add a little bit more to that answer.
I mean, it's the linearized model for the multiply type of the cobordism category.
Yeah. So
the cobordism category, if you make a category out of cobordisms, then it has this as its multiply type.
Yeah.
In particular, pi minus one. So pi minus one is a cobordism group.
Yeah, so pi minus one is because so it does relate to cobordism categories. Yeah, but I was just sorry.
Which paper by Christian Priest?
He has one that's literally called invertible TQFTs. Yeah, so, and that's where he does his work. It's long though. It's like something like 70 pages, so lots of details. Okay, so yeah, so I just wanted to mention this a little bit more than for going into deep considerations there, or just to give a little bit of the framework of where we are standing. Like the project I want to talk about stands more like on this geometric side. So again, we're going to be doing relations or trying to understand relations to invertible TQFTs, but we're going to try to understand the story from the geometric side and making it see how the SKK groups and the SKK invariants fit into this picture. So just to name and to give the whole framework, this geometric interpretation of invertible TQFTs was in a sense not quite written, but first discovered, or the first people who thought about this were Stefan Stolz, Craig, which came alphabetically earlier. So Craig, Stolz, and Teichner. So they actually did some work on this, and then I took up this project with a student. So we wrote out kind of like a very accessible version of the project, and then, well, we'll get there, but then we encoded things into an exact sequence, and we figured out that split exact sequence. So we'll get there as part of this story. But the initial idea of the connection between the SKK, the geometric interpretation of cut and paste, and invertible TQFTs was due to this team of authors. Okay, so we're going to relate this to topological quantum field theories. So let me first of all give a few definitions, just in case the audience might be quite broad. So not to skip any, not to lose anybody. So what is a TQFT? So an n-dimensional TQFT is symmetric monoidal functor that does what? So it's going to assign to each n-1 dimensional manifold. Now the dimensions here are important. You're saying that your functor is n-dimensional when you're thinking about, well, like the picture is helpful maybe. You're thinking about the dimension of the bordism right here is your n. And the n-1 dimensional manifold would be boundaries, which are obviously one dimension lower. So to each n-1 dimensional manifold, your functor assigns a finite dimensional vector space. So like looking back into the picture, this is one of my n-1 dimensional manifolds. This right here would be some finite dimensional vector space. And same thing on the other side, another boundary, another n-1 dimensional manifold, so another finite dimensional vector space. So that's like on the boundaries, like on the n-1 dimensional manifolds. What happens on the bordism level? So the bordism is taken by the functor to be a linear map. So that's why it's kind of important to keep track of what dimension we're talking about. So you're going to see your functor applied to manifolds of different dimension. Everything has to be inside of a certain context of a certain dimension. If your manifold is a bordism and it's n-dimensional, it's going to get mapped to a linear map. If you're talking about an n-dimensional TQFT and you're applying it to n-1 dimensional manifolds, what you're getting is vector spaces. Vector spaces, linear maps, you kind of like get this algebraic mirror of what's happening in the geometry. Okay, so Atilla gave one of the very first approaches, like topological approaches to TQFTs was given by Atilla, and he gave this axiomatic approach. So from all of those axioms, I'm going to just pick out just the ones that are like super key for getting the idea of what our project is. Of course, there are more axioms, but we're not going to worry so much about them. So what are the key axioms? So the key axiom is that one of them is that when you glue cobordisms, like you're seeing in the picture here, you're seeing two glued cobordisms. They are glued via along a certain boundary, this sigma 1 boundary. So when you glue that is going to correspond to composition of linear maps. Now let's analyze the picture for a second. I have my n-1 dimensional manifolds. This is n-dimensional, n-1, n-1. So if I look at what my functor is doing, so I get vector space, vector space, vector space. And then the first chunk of the cobordism gives me a linear map. And then the second chunk, the cobordism n, gives me another linear map. And then, of course, I can compose those. But what I really need is that, the functor applied to the whole thing, the functor applied to the glued cobordism mn, so this means m glued to n, has to give me the composites of the two linear maps. So that's one axiom from the TQFT. Another axiom that we are going to need.
Carmen,
yes?
What is your source category? Is it cobordism category? Is it homotopy cobordism category? What's it?
It's just cobordism category.
And your target is vector spaces?
Vector spaces. Mm-hmm.
And you have a functor from?
You have a functor
from topological category to the usual category, or how?
Yes. Let's see. I mean, I don't have a TS paper in front of me right now, but that's how I understand it. I think that's correct.
Yeah. Okay.
I think originally people didn't think about the topology, so they thought about like sort of taking diffeomorphism classes. But if your target is like a discrete category, then like it just factors through taking a multi category.
I mean, you don't need all of that technology to be able to make the connection. So I kind of like we just worked with the original the axiomatic approach of Atiyah. But yeah, of course, we know a lot more right now with all the the topology and everything. So you could do other things.
So in Fried Hopkin, they like have a topology, I think, on the target as well.
Yeah,
where they work in the multi theory.
Yes. Yeah. I mean, depends on what you want to do. Okay, so going back again to the axioms, Atiyah's axioms. The second one that we really need is that the empty manifold gets sent to the ground field. So that is important. And why is that important for us? Well, let's look at this picture. So if we have our cobordism right here, well, how do I now? Okay, so now I have an empty manifold, and I have another empty manifold. How am I understanding this? So I am understanding my closed manifold as a bordism from empty to empty. And why am I allowed to do that? Well, because the dimension of the empty manifold depends on whatever context I am in, and I can choose whatever I need. So I am choosing in this sense to have my empty manifold play the role of the n-1 dimensional manifold. So yeah, I do get a cobordism from something closed to something closed. And when I translate to the algebra via the functor, what I'm getting is, well, the ground ring right there, ground ring, and I'm getting a linear map. And that linear map, it's a good way of thinking of that linear map is to identify it with a certain scalar. Because if you identify that with a scalar, then what you're saying is you are taking a closed manifold and having your TQFT spit out a scalar. And what is that? Well, that is a manifold invariant. And that is going to be one of the crucial ideas when we try to make the connection between TQFTs and cut and paste invariants. So this is an important notion right here, understanding a closed manifold as a cobordism and understanding it as you're attaching a scalar to a manifold via your TQFT. Okay, so what do I need? So it's not all of TQFTs that we're going to be talking about. We just need to understand invertible TQFTs. So if you're thinking of the whole category of TQFTs, of n-dimensional TQFTs, the notation we gave ourselves for that was this n TQFT, your ground ring is K. Well, that category has objects n-dimensional TQFTs. And the morphisms, since each TQFT is a functor, the morphisms between them are going to be natural transformations of those functors, which are TQFTs. Now, we don't want all of them. We just want the invertible objects in that whole category. And that's what's going to be the invertible TQFTs. So what does it mean? Well, it means that your operation here is tensor product, of course, because symmetric monoidal category. So your notion of invertible is that you're going to have a TQFT. You're going to have a TQFT, and you're going to be searching for its inverse in the sense that what you're searching for is that when you take the tensor product of the two, you're getting the identity TQFT. And the identity TQFT is just going to send things to ground ring, and then this is going to be the identity linear map. So that's what you're searching for, a TQFT that has an inverse. And not all of them do, but some of them do. One important property of anyone that can do this is that your TQFT sends the boundaries to one-dimensional vector spaces, because tensor product will take the product of the dimensions of the vector spaces. So if your functor T maps something to, I say, a two-dimensional vector space, then you're not possibly going to be able to get back to something which lowers the dimension of the vector space. So invertible TQFTs necessarily are going to need to be the n-1 dimensional manifolds we have to be sent to one-dimensional vector spaces. So that's an important an important idea right there. So I just mentioned this one. An invertible TQFT is a TQFT such that every when you apply to one of the boundaries, you get a one-dimensional vector space, and that every linear map, every vortism, gets mapped to something which is a linear map which is invertible. So those are going to be our two key ideas of what an invertible TQFT is. They form a group and a tensor product, which again, this is kind of a little bit invented notation from our paper, but essentially it says it's all. You have the notion of the ground ring, you have the dimension of the functor, and the symbol up there is just to remind ourselves that we do have a group. So there is a group of invertible TQFTs. Now we're approaching now the result. So the result is phrased in a slightly informal way that all invertible TQFTs determine SKK invariants. In other words, you can form this short exact sequence where the middle term is our group of invertible TQFTs. Then this home, well, what is this home? This home is SKK invariants, because you're taking SKK things and sending it to, they're maps from whatever your manifold, your SKK representatives are, to some values, so that those are invariants. Because of there maybe other choices, but we chose to work with R as our ground ring. So it's a good idea to have the invariant take values in the this multiplicative group of positive reals. And then, well, it's an exact sequence. This has a kernel. What is the kernel? Well, it's good. It is actually what you could think it is. It's all of those invertible TQFTs that when you think of them as SKK invariants, they're just going to be like the trivial ones in the group. So just the one, or the ones that take value one or minus one of those closed n manifolds on the morphisms. Right. So this is kind of like a very nice phrasing of the connection, but maybe I want to give you a very quick idea of how the proof works. So we are going to be thinking of these two cut and paste equivalent manifolds. Okay, so so I have M1 and M2. Those are those two pieces, and now I have these two pictures are cut and paste equivalent. It's just I've thickened the gluing a little bit, so we can see a little bit more. So that's why that CF is just a mapping cylinder. So that's like the gluing done a little bit thickened, but there's still two cut and paste equivalent things. One is pasted via some diffeomorphism phi, gives me the central part is a mapping cylinder of phi. Actually, there's a little typo right here. I'm going to fix it. So this is phi, and this is psi. Okay, so those are two cut and paste equivalent things. And now I'm going to do the work of applying the TQFT. So, one of these invertible TQFTs is going to take this manifold. It's going to take this manifold, and it's going to do, well, it's a linear map. So the whole thing is going to be a linear map, but it's a composite. So it's a linear map, which is a composite of this piece, and the central piece. And similarly, well, now we're doing multiplicative. My TQFTs are invertible, so there's no risk of putting that in the denominator. But if you see what's happening in the denominator, is exactly the same story. I have my M1, my central part, and my thing here. So it's the composite of those three morphisms. So that's what it is. And I'm abusing notation a little bit. We talked a couple of slides ago, we talked how it's very good to think about the TQFT, the functor on a closed manifold, not exactly as a linear map, but as a scalar. So this is how I'm interpreting this notation here. In our paper, it's actually written very carefully when we mean scalar, when we mean actual linear map. But I thought that for the slides, it was like, it's too many symbols. So these are scalars. Okay, so by one of the axioms, I know that I can decompose this in tau of the first thing, tau of the cylinder, tau of the other piece. So that's the first, what the first equality does. And now, well, and now I see scalars that go inside, so I can get rid of them. And I'm left with this this expression here from in the purple box. And the expression in the purple box, very interestingly, is just, well, it's just what is happening on this like slightly thickened gluing information, which is the mapping cylinders. So what am I seeing there? I'm actually seeing an expression that only depends on the diffeomorphisms. Sorry, a bit again typo. On the diffeomorphisms phi and psi. So it's exactly what happens with the SKK invariant. You remember the expression for the SKK invariant? It was like, you apply your invariant to the two SK equivalent things, and what you get is not exactly zero. You got your error term, which only depends on the diffeomorphisms, and this is exactly what you're getting. So that's kind of like the essence of why you're getting this connection between the TQFTs and this cut and paste invariants. We're almost out of time, but just to like give you like an idea of like another part we thought was pretty interesting. Like once you formulate the short exact sequence of this connection between the group of invertible TQFTs and the SKK invariants, you can ask yourself, does the sequence split? And yes, it does. So that's proven in our paper. That's kind of like again another one of these longer proofs. It's kind of like I would say it's one of the difficult part of the paper. I mean, difficult to some extent. Yeah, so it's you do get the splitting. You do not get. Let's see. So what you do not get, so there are choices that you need to make, but that doesn't affect the fact that you do get some splitting. The splitting depends on choices, but it exists. So yeah, so the exact sequence splits, and that was kind of like the main theorem in this whole story. So if anyone wants to have any more details, this is our paper, and thank you so much for listening.
Yeah, thank you very much, Carmen. Really nice talk. So, questions?
Yes.
Renee?
So in this splitting, does that somehow use this Caver semi-characteristic as well?
No, it doesn't. It doesn't. Let me actually see. No, it doesn't. It just no, it doesn't. Unfortunately, not. I mean, the Caver semi-characteristic appeared in the sequence that related SKK with Bordism, but here we are already talking about a very different situation with the groups. It does feature somehow because when we are saying here. Home from SKK to R, well, those are the SKK invariants. So all hidden in one of those homes is going to be the semi-characteristic is going to be one of them. Oh, I used K. This is another notation. Same notation for the same thing. So the semi-characteristic is going to appear there, just as the signature or the Euler characteristic, and so on, so on. Those are the homes that you're seeing there, but it doesn't appear as part of the splitting.
Another questions? Not, I would like also. I have two questions. Once is in the coordinates category. There is this paper that of the fundamental group of the classifying space of the coordinates category. where really you are working on the category of fractions, and there are some relations that you can find in one of my papers, that there is a way to find the category of fraction of the covariance category in terms of some relations. And these relations I found in your paper. Is this way of how you can construct this section? So this section you prove some lemma, the 5.10.
Yes.
And that relation is exactly the relation I need for.
Oh, cool. I hadn't realized that, but now I'm super curious. So can you email me your paper later, or point out which one?
Yeah. So this is the relation 5.20 is
okay.
that. Do you know that the TQFT are functors, they are symmetric functors, but they are in correspondence with the functors that have a start from the category of fractions. And that relation is exactly that one. So, yeah, I would say. And my next question is the second one is for the three of you, Renee, Julia, and Carmen. Yeah, really, I have in one of my in my paper, I have some exact sequence that is really almost similar with this exact sequence of SKK. So you put in the middle the fundamental group of the covariance category, and then you can send to the Bordis group, yeah, and there is the kernel of that map is some group generated by the sphere.
Yeah.
So, and it is possible that you always consider closed surface up to the SKK relation, or SK only. But what is the obstruction to construct a covariance category with that relation, not only in the closed part, to construct a covariance category with the subindices SK and also SKK. It's not well defined.
The closest that I know is
maybe like through this vector field borders, and you could construct like a border category with vector field borders.
Maybe. Have you looked at this paper by Bergstedt and Svein and one more person? There's a paper which does a very, very careful very careful exposition, or and trying to understand the connection between SKK and vector field bordism, as cobordism categories, I think. But yeah, it's probably not very well studied in general in the literature. What you're saying is something a little different, I think. And the closest that I can think of is the MTSO somehow also been a cobordism spectrum, and it's been pi node of that is SKK, but yeah, it's not. I think that what you're saying is something a little different, and I think you're right that there's no real good understanding of it.
It's not well defined that I put not only closed, but I put some open with boundary, and I put the SK relation there, and then I send the gluing of two covariances is going to be the gluing of that covariances up to the SK relations, and this will form a covariance category with SK. The reason is that because when
did you write this up, or did you have some a draft of this? Because maybe you can send it and we can look at it. And
no, the reason is because of that exact sequences. Instead of you write the Bordis group, you will write the Bogomolov multiplier. And we are trying to find the Bogomolov multiplier in higher dimensions, and maybe that could be a good try.
So another interpretation of the exact sequence is that it comes from the Gnauer vibration of cobordism categories with boundary, and then it's the long exact sequence in homotopy of that So that's the same exact sequence. Maybe that helps for interpolation. I don't know.
Alice, but can you repeat what group are you considering? I'm not sure I understood.
Yeah. The first one is that.
So is it first of all, is it a group or is it a category that you're talking now?
Instead of considering closed bordings with SK relation, you can just take all the category of covariance, and then you consider the quotient up to SKK relation. My question is that possible? Is that category well defined?
So you take the quotient category, but instead of like quotienting by diffeomorphism, you want to quotient also by column-based equivalence. But how do you deal with the boundaries? Like what do you do column-based equivalence on the morphisms and then leave the boundaries preserved?
Yeah. The boundaries. I think you don't make SK relations on the boundaries. Yeah, maybe that could be a problem on the boundary.
Well, I mean, I suppose so. I mean, if you think about like, I guess you could like quotient the Hom spaces or the Hom sets by a cut-and-paste relation that preserves the boundary.
Maybe that not will be well defined, because when you are doing SK relation in the gluing, you need the quotient on the boundaries. So
yeah, I mean, you could try to like quotient the objects by SK equivalence, but then I don't know how you define the morphisms such that they're like well defined. But there could be a way of quotienting the morphisms in a way as well. But because the morphisms are manifolds with boundary, I mean, they have you have to have some sort of relation that extends kind of paste equivalence on the boundary. I mean, like you can't always, like if you take like the identity morphism, so like there's not always a cobordism between two kind of based equivalent manifolds.
Yeah, it's with the SKK it's different, but with the SK it's like it's a non-existing relation there. I mean, they don't map either way.
I think I have to think more my question.
Yeah, I mean SKK maybe, but like SKK is sort of bigger than cobordism, so
yeah.
But maybe if you add a vector field or something to your bordisms, then it might extend to like a category of which phi naught is SKK instead of bordism. Yeah. So it's like a bigger than bordism.
It has. I mean, it has to do the same thing because SKK is just as I said, like the different interpretations of SKK. Vector field bordism is one of them. So just by adding the Euler characteristic as one of the bordism invariants, that should give you the right thing.
Well,
interesting.
Yeah, I think the boundary will be the problem. The boundary.
Yeah.
Well, thank you.
Yeah, the boundary is always a problem.
Yeah. Well, if there are no other questions, yeah, thank you very much, Carmen.
Thank you.
Thanks for a beautiful talk.
Thanks.